Timber pathology is the science of reading the hidden language of wood. Every grain, every angle carries a message about strength and vulnerability. The danger lies in the potential failure mode, shear rupture under pressure. The timber can fracture suddenly, its integrity lost in an instant. This is why timber pathology matters. By visualizing biological origins and structural impacts, we uncover the anatomy of resilience and weakness. Every deviation, every rupture is a reminder that wood is not just material, it is a living history. And to build safely, we must respect its story. Timber carries the silent record of a tree's life, and in pathology, we uncover the four great categories of its imperfections. Grain deviations. These are the misaligned fibers, often called cross grain. They weaken the wood's ability to bear loads, making beams more prone to splitting. Even a small deviation can reduce strength by up to 50%. A reminder that alignment is everything in structural integrity, not formations. The traces of branches locked into the bowl. Nuts can be beautiful, adding a character to furniture, but in construction, they are weak points. Their geometry interrupts the smooth flow of fibers, creating stress concentrations that can fracture under pressure. Internal tensions, the invisible stresses within the wood, growth stress and reaction wood from form when trees resist wind, slope, or gravity. These tensions remain hidden until sowing or drying. When boards warp, twist, or crack, it is nature's memory of struggle carried into the timber. Ruptures and inclusions, the scars of trauma, of brushness, pitch, pockets, or bark inclusions tell of storms, wounds, or foreign matter trapped in growth. These defects compromise durability, sometimes allowing decay or insect to enter, turning strength into vulnerability. Together, these categories remind us that wood is not inert. It is alive with history. To study its pathology is to respect both the resilience and fragility of trees, and to ensure that what we build honors the materials nature. Grain is the silent architecture of timber, and its taxonomy reveals both strength and weakness. We begin with a straight grain, fibers aligned perfectly along the tree axis. This is the ideal, the mark of stability and resilience, where wood carries loads with maximum efficiency. But when fibers deviate, we encounter cross grain. This misalignment is the root of many defects, reducing strength and making timber prone to splitting. From here, three distinct forms emerge: diagonal grain, a milling defect. It occurs when timber is sawn at an angle to the natural grain, creating slanted fibers. Though man-made, its impact is severe. Boards warp, weaken, and lose structural reliability. Spiral grain, a biological defect, as the tree grows, fiber twist helically around the trunk, often in response to wind or uneven growth. This spiral reduces stability, making beams more likely to distort under stress. And finally, interlocked grain, a complex pattern which spiral directions alternate layer by layer. It resists splitting, but at a cost, machining become difficult. Surfaces tear, and the wood's hidden tensions reveal themselves in unpredictable ways. Together, these grain types remind us that timber is not uniform. It is a living record of growth, environment, and human intervention. To understand them is to respect the balance between nature's design and our use of it. In timber, the grain is more than a pattern. It is the backbone of strength. When fibers run parallel, we call it normal grain. Here, the load travels smoothly along the strong longitudinal fibers, giving wood its maximum resilience. But when fibers deviate, we encounter cross grain. The slope of grain, even a slight angle, forces weight across the weak middle lamella of the cells instead of along their natural strength. This misalignment can reduce structural capacity by half, making a beams more prone to splitting and failure. Cross grain is not rare. It can arise from natural growth stresses, nuts, or even milling errors. For engineers and foresters, recognizing it is critical. A board with a slope of grain beyond 1 in 15 is often considered unsuitable for load-bearing structures. This is why diagnosing grain is more than inspection. It is protection. By reading the hidden geometry of wood, we safeguard bridges, homes, and lives. Timber pathology reminds us strength lies not only in the tree's growth, but in our ability to respect its design. Every knot in timber is a story frozen in wood. It begins with the cone, dense, lignin rich tissue where the branch pushes outward, anchoring itself into the trunk. This is the heart of the knot, the point where branch and bole meet in struggle for space. When the branch is alive, we see the tight knot origin. Here, fibers fuse seamlessly within the trunk, creating a strong bond. These knots may add character to the wood, but they also disrupt the grain, concentrating stress and reducing strength in beams and boards. But when the branch dies, the tree continues to grow around it, forming the loose knot origin. Unlike tight knots, these are weak, often encased in bark or air pockets. They can fall out during milling, leaving cavities that compromise durability and invite decay. Knots are more than imperfections. They are biological records of growth, survival, and loss. For foresters, carpenters, and engineers, understanding their anatomy is essential. Each knot reminds us that timber is not flawless. It is alive with history, and its strength depends on how we read and respect its story. Knots are not just marks in timber, they are the living signatures of a tree history. The knot diagnostic table helps us read these stories with precision. First, splay or spike knots. These are sound and integrown, formed when living branches fuse tightly into the trunk. Their geometry is distinct, elongated or spike shapes that remain structurally secure though they disrupt the grain. The pin nut clusters, often called catpos. These are tiny, less than 5 millimeters, but grouped together, they create localized anomalies. Though sound and intergrown, they weaken the uniformity of the wood, leaving behind a spotted record of branching. The encased round nut. Unlike the sound nuts, these are unsound, dead branch tissue encased by the growing trunk. They appear around, but their bond is loose. In milling, they can fall out, leaving cavities that compromise strength and invite decay. The quadrant of unsound clusters, rarely illustrated but critical to recognize. These are groups of dead nuts, fragile and unstable, often hidden until the timber is cut. Each nut type is more than a defect, it is a diagnostic clue. By reading their geometry and connection, foresters and engineers safeguard the structures we build. In timber pathology, nuts remind us that every board carries the memory of branches once reaching for light. Trees carry the memory of their environment, and sometimes that memory is written in stress. Sudden growth shifts from drought to rapid hydration create internal tensions. Cells expand unevenly, forcing cracks deep into the trunk. Uneven maturation between sapwood and the heartwood adds another layer of strain. As the outer layers grow faster than the core, stresses accumulate, waiting to release. And when canopies are thinned and sudden release of pressure changes how a tree distributes its weight. What was once balanced becomes unstable. The effect is visible in two forms of separation: heart shakes, radiant splits that burst outward from the pith, weakening very center of the tree, and ring shakes, tangential separations along growth rings, peeling the tree apart layer by layer. These fractures are not random. They are the scars of survival. To diagnose them and to understand how environment shapes timber and to respect the delicate balance between growth and strength. Trees do not stand passively against the forces of nature. They adapt. And in that adaptation, they form what we call reaction wood. In conifers, the answer is compression wood. Its cells are packed with lignin, darker and denser than normal. This makes the timber harder, but also unstable. High moisture movement, leads to severe shrinkage, warping boards unpredictably. What looks strong can betray its builder. In broadleaf trees, the response is tension wood. Here, fibers grow with a gelatinous secondary wall rich in cellulose. It pulls against gravity, helping branches resist sagging. Yet for us, this wood is unreliable. Its properties shift and strict grading often rejects it. Reaction wood is nature's engineering, a survival mechanism against wind, slope, and imbalance. But for foresters and builders, it is a warning. These hidden zones remind us that timber carries the scars of struggle, and only by reading them can we respect both the resilience and fragility of the forest. When storms rage or lightning strikes, trees endure forces beyond their limits. On one side of the trunk, fibers are stretched in tension. On the other, they are crushed in compression. Normally, wood bends and recovers. But when the force is too great, the compression side buckles and the tree suffers what we call brushness or thunder shakes. This failure is instantaneous, a traumatic collapse where fibers fracture across the grain. The diagnostic cue is unmistakable. Jagged, irregular breaks that destroy tensile strength and bending resistance. Once brushness occur, the timber is compromised, no longer able to carry its intended load. Brushness is more than a defect. It is the scar of a violent encounter with nature. For foresters and engineers, recognizing it is vital. It reminds us that timber is not invincible, that the every board carries the memory of storms survived and stresses endured. Not all timber defects are vast fractures. Some are subtle anomalies hidden in pockets and surfaces. First, the pitch or resin pockets, found mostly in conifers. These are deposits of liquid or crystallized resin trapped within the wood. While they don't drastically weaken strength, they ruin finishes, bleed through coatings, and cause rejection in appearance grade lumber. For carpenters and builders, they are a reminder that aesthetics matter as much as structure. Then the bark pockets and wane. Bark pockets form when cambium is trapped around a dead branch in case as the tree continues to grow. Wane, on the other hand, is the remnant of the log's rounded surface left on sawn timber. Both create breaks in continuity, interruptions that compromise structural reliability and reduce usable yield. Then localized anomalies may seem minor, but they carry weight. They remind us that timber is not flawless. It is shaped by growth, stress, and survival. To diagnose them is to protect both the beauty and the strength of the wood we use. Every piece of timber carries its own story of strength and weakness. The defect impact synthesis shows us how those stories translated into risk. In the green zone, we found only minor imperfections, pin nuts, small resin pockets, and slight color changes. These are aesthetic flaws, harmless to strength, but enough to reject wood in appearance grade applications. The yellow zone reveals moderate compromise, sound tight nuts, mild reaction wood, and cover nuts disrupt fiber continuity. The timber still holds, but its reliability is reduced, demanding caution in structural use. And then comes the red zone, the realm of catastrophic failure. Thunder shakes, severe cross grain, and clusters of dead nuts or bark parquets. These defects destroy tensile strength, bending resistance, and continuity. Timber here is unsafe, a hidden hazard waiting to fail. Grading timber is more than inspection. It is engineering. It is the art of balancing nature's biological variance against the tolerance required for safety. Every beam we trust must first be read, diagnosed, and respected.